problem we're going to solve now is 29.30. You can see on the right, there's a magnetic field, and all those points has an initial magnitude of 0.75 Tesla. They give that to us in the problem. 0.75 Tesla. Okay. And then they tell us that it's going to be the space inside of a long, thin solenoid. Okay. And they tell us that that rate is decreasing. So the rate is getting smaller. Okay. Then they ask us what's the shape of the field lines inside that colored circle. They ask us what's the magnitude and direction of the field when there's a radius 0.1 meter. Then they ask what's the current in the ring, what's the EMF, and what would be the EMF between the ends. Okay. So they ask us a bunch of different things here. Okay. First, they ask what's the magnitude and the direction of the field at any point. So, and that's what are the direction of the electric field? Well, we know that if there's a changing magnetic field, it's going to induce a bunch of electric fields that are all going to go like that. Okay, they're all going to have lines like that. But what direction are they going to go? Well, that's the trickiest part, which is what direction are they going to go, clockwise or counterclockwise? Those electric fields. Well, again, we're going to go back to what we did before with our magnetic flux. In this case, our magnetic flux decreases because we have our rate is decreasing, okay, and our field goes into the page. That means our induced field should also go into the page. That means that if there's a current that went around, the only way to make that current, one that goes into the page, again, I'm grabbing onto that cable, or really to that loop, but it could be anything I'm grabbing onto, would mean that my current would be clockwise. And the only way I could get that would be to have a magnetic field that pointed in the same direction. So the lines are going to go like that. So that's A. In BS, we got the magnitude, we got the direction, okay, but they want the magnitude. Well, I know that the way that I'm going to come up with that is by saying that the EMF is going to be negative E dot dl. And EMF is something we already know how to find. We can just set that equal to the change in flux over change in time. And in this case, the flux part is actually not the hard part to find. Okay? We're pretty good at that now. We know that in this case, the area inside that ring that's 0.1 meters away. Remember, we're doing the 10 centimeters, so it's this ring here. The area, remember, this is going to be the area times dB dt. So the area is going to be, because it's a circle, it'll be pi times 0.1 squared. And dB dt will just be the amount. It'll be the change in the flux. It won't be the initial magnitude. It's just going to be this number here. So it's going to be negative 0.035 Tesla per second. This is meters, by the way. So if I take out my calculator, multiply all that stuff out. So I take pi times 0.01, because that's 0.1 squared, times 0.035. Remember, I have a negative in front of this. Okay. So I multiply all that together. I got 0.0011 volts. So that's the left side. Okay. Or sorry, that's the right side. That's the change in flux over change in time. But for EDL, that's the part I have to do next. Or that's going to be the path around here. Well, that's not hard to find because it's just a circle. And we know the path around that. It's just 2 pi r. So that's going to be E times 2 pi times 0.1 meters equals our 0.0011 volts. That means E is going to be 0.0011 divided by all that stuff. I'm going to divide those. I got an answer of 0.00175 volts per meter, which is going to be the same thing as newtons per coulomb. That's A. This is B. There's a C, a D, and an E. C says, what's the current in the ring if the resistance is 4 ohms? Well, that actually turns out not to be terrible because we actually found what the voltage was. So the current is just going to be the induced voltage divided by the resistance. So it's going to be 0.0011 volts divided by 4 ohms, which if we divide those out, 0.0011 divided by 4, we get an answer of 2.75 times 10 to the negative 4th amps. D turns out to be, it says, what's the EMF between points A and B on the ring? So here's A and here's B. Well, we can do it the same way. We go back to E dot dl equals negative d phi dt. Okay. And we actually do more. We actually know the answer for the whole thing, for the whole ring. We know it's 0.0011 volts. So if we're just looking between this point and this point, that's just going to be half. So the half is going to be 0.0011 divided by 2, which is going to be 5.5 times 10 to the negative 4 volts. That's for D. Now for E, they do something weird. They say, let's say we take this whole thing. I want to erase all these marks. And then they separate it slightly. So they're going to take it and they're going to make just a little bitty mark. We're going to separate it, let's say right here, like a little sliver. And they're going to say, what's the EMF like between the 2 points, like this point and this point. And again, I didn't draw it quite close enough. Let's see if I can move this puppy so it's over here a little bit. And it doesn't look like I can't, okay? But you get the idea. Like right over on the edge there. So that actually turns out not to be hard either, okay? Even if I cut it and separate it slightly, I'm gonna get it's still gonna be the whole ring, the same as before. So the voltage is still gonna be 0.0011 volts. So I'm gonna have the same voltage between the ends, even though I separated the ring slightly. I'm still gonna have the same area pretty much. I'm just gonna have a difference in voltage across the edges.